Okay, so we should see the little record button in the upper left-hand corner of our Zooms. And let me jump back into the slides. Okay, so just for the benefit of the recording, we're gonna talk today about quantitative engineering analysis that is requested in the preliminary design report. And of course, we're now in the down selection to preliminary design module. It's, I think, the sixth module out of 8 in the class. So we're getting close to the end. And I'm going to share with you guys an example from 2019 fall, where one of the groups, and these are folks that were working on a 3D bioprinter, so similar to the project that you guys have. There was need for a very small pump, and so I want to walk through with you guys how that was designed. We do have a few items in addition to that. So this is what we're going to do overall today. We're going to talk a little bit about the IP disclosure assignment, because I've had enough questions on that I wanted to clarify for everybody. We're going to do this engineering analysis that I just described. And then there's going to be an in-class activity on Tuesday, the 21st, which I call the cross-pollination activity, which I've never actually done before. This will be the first time. And I want to give you just some instructions so that you're prepared for class on Tuesday, so that nobody is surprised. But so let's first spend just a few minutes talking about the IP disclosure assignment, which is also due in parallel with the preliminary design report on July 26th, so Sunday, July 26th at 11:59 p.m. And I guess where I want to start with this is to point out that IP disclosure has always been part of the preliminary design report, but up until spring 2020, they were part of the same assignment, right? So intellectual property disclosure was just part of what you did as you submitted your preliminary design report, and we're now, this class has evolved enough, and students are getting kind of creative and bold enough that you are, in some instances, truly generating new and novel ideas. And so in the spring, upon recognizing that some students actually had invented things that might be valuable intellectual property, I intentionally pulled the IP disclosure portion of the preliminary design report out of that assignment, and I made it its own separate assignment, so that it would be very easy to just, as you guys will see, just take what you've done for that sort of now separate assignment, and submit it to UF if it's appropriate to do that, to the UFINNOVATE office. So let me kind of walk through how this is going to go. So we're now, so previously, like in previous years, a lot of times the 4501 students would be working on kind of neat, fun projects, but that were not necessarily potential products, right? So for example, there was a neat project a couple years back where the students made kind of a miniature autonomous hydrofoil boat thing, but it was a one-off thing. It didn't really have, at least at the time, any commercial applications. It was just of interest to a particular faculty member. They've worked on coffee makers. There was a coffee machine that was a couple years back. There was an automated gripper that was a couple years back. So they were neat projects, but they did not necessarily have valuable intellectual property associated with them, because either they were projects for a specific application that didn't have kind of a wider value, or they were just kind of what's the right word? I don't want to say toys, but just kind of neat little things to play with, but not really, it had very little potential maybe for commercial applications. So we've now kind of changed, right? So when we select projects now, we select projects that, yes, are beneficial to PIs, to the principal investigators of the research laboratories in the department, but we also try to stay away from projects where there's only one person in the world that would potentially use it. So we want to actually select things that have the potential to be commercialized and become products, because that would be a neat thing probably for some of you guys to be able to work on. So it's both beneficial to the PIs, but also increases the University of Florida intellectual property portfolio. And so any intellectual property that's invented at UF using UF resources, with very few exceptions, is typically owned by the university. And the way that the university kind of keeps track of these inventions is the inventor or plural inventors disclose those inventions to the UF Innovate Technology Licensing Office. And so this project is one of those examples, right? I mean, you guys are UF students, you're taking a UF class. I'm a UF faculty member, I'm sort of guiding the process. And so this, oh, hang on, sorry. This is very clearly kind of a UF resourced project. And so anything that you guys develop, by all rights, should be disclosed to UFINNOVATE. UFINNOVATE has a disclosure portal, an online portal, and in sort of building this project with them, I discovered that the portal is accessible to UF faculty and to UF staff, but it's not accessible to UF students unless there's some sort of prior notification, right? So unless either a faculty member, a staff member, or a student who's invented something lets UFINNOVATE know that they've invented something and they want to disclose, in which case then UFINNOVATE has to go in and actually create one by one the individual student accounts. And so in kind of talking through them how to do this in such a way that we could provide a mechanism for you guys to disclose, they didn't want to just load all, normally 150, 160 students enroll in this class. They didn't want to go in and like manually have to add all of those students. And so we came up with a protocol that I'm about to describe that kind of makes their lives easier, but also gives you guys a chance to disclose if you've truly invented something. So there is this disclosure portal. I've got a screenshot of it up here, but you guys, as UF students, don't have access to it. So what we've done is I've taken all of the questions from the UFINNOVATE intellectual property disclosure form, which is, again, just an online form that you fill out and submit when you want to submit new inventions to the university. So I've taken all of those questions and I've just dropped them into this intellectual property disclosure assignment, which if I can pull it up here, let me just grab it. Where is it? I did have it. One second. Where did it go? Oh, okay. Here we go. Yay, technology. Okay, so this is our Canvas page, and then here's the assignment right here. Okay, so this is the IP disclosure assignment. This is the PDF version. You guys can grab this off of Canvas if you want to. So all of these questions, export control questions, conflict of ownership questions, inventor questions, description, prior art, these are the exact same questions with the exact same wording as appear on the UFINNOVATE intellectual property disclosure web form. And so what I'm having you guys do is essentially just create like a Word document, right? So I would just literally open a Word document and I would just copy this content into the Word document, and then I would answer each one of these bullet points or each one of these questions just in that Word document, and then you can convert it into PDF and you can upload it into Canvas. And so that's how I would suggest doing it. The process after that, if I jump back in here, so the process after that is once you submit that PDF of all the answers and responses to the web form effectively into Canvas, I am going to just go through all the submissions and let individual groups know. There's 7 of you. Let individual groups know whether you have invented something novel. So this was the UFINNOVATE office wanted some sort of filter. They didn't want like 23 disclosures, because then they would have to go through all 23 disclosures. And more often than not, students don't actually end up, at least undergraduate students, don't end up actually inventing things. They generate a lot of good ideas, but those ideas more often than not already exist. And so even if you've done a literature search and haven't found them, more often than not, there's something already out there that would already be either patented or kind of already disclosed in the open literature that would prevent your intellectual property from being protected by UF. And so I'm going to go through, I'll probably grab Brandon and pull Brandon Tran, who's our grad TA, in as well. And we'll just walk through all 7 submissions and see if there's anything in there in our judgment that is novel. And if we find any group that has generated something that's novel intellectual property, we will let you know just by alerting the group. And if we don't find anything, we'll also let you know, just so that we close the loop on that. And if you disagree, that's great. Just if you disagree, we can move forward with the process anyway, and we'll see what happens. But for any group that has in kind of my opinion and Brandon's opinion, invented something novel and put it in their disclosure, I will then go ahead, after I alert the group, I'll go ahead and alert the UFINNOVATE office and give them the names of the inventors, so the names of everybody in your group. They will then create profiles, right, accounts for you guys on the UFINNOVATE technology transfer site. So you guys will then be able to log in and make your IP disclosures officially, formally through the UF Tech Transfer office. And so you guys will be able to go in. And so here's why I set up the assignment the way that I did, is because I don't want to create a bunch of work for you guys. I know that you guys are busy. You have a lot going on. Your time is valuable. And so instead of having you like basically write a whole nother disclosure, the reason that I just copy pasted the questions out of the Innovation Hub Tech Transfer web portal into the assignment is because it allows you to effectively do the same thing in the opposite direction. So you should be able to go in and just copy your answers for each of the individual questions into the Tech Transfer portal web form, and you won't have to change anything, because you literally just copy paste. And then when you've got everything pasted in there, you just hit the submit button and you're done. So it should take no more than 15 minutes of one group member's time to transpose what you did for the assignment into the web portal. And this, to sort of close the loop on the explanation of why this is a separate assignment, is in the past, when the intellectual property disclosure was part of the preliminary design report, students would end up like writing a whole bunch of extra stuff in there, answering questions that they didn't need to answer for an IP disclosure, because they were trying to write a good report. And the groups that did end up having to disclose had to do a bunch of extra work to like rewrite everything so that it was basically sanitized for the tech transfer office. And so by separating the 2 assignments and making this one separate, the intention is not to give you more work, but to give you less work. Even though you've now got 2 assignments to deal with, it's actually less than what was previously requested. So once you do the copy paste and the submit, then the final step is that staff at the UF Tech Transfer Licensing Office will review each of those officially submitted disclosures and reach out to each individual group if the disclosed intellectual property shows promise for further scrutiny by UF for for protection, eventually a patent, for example. And I've had actually two groups now in the past year as we've done this get to that point where they've actually had the conversation with actually three groups because there was two in the spring and one in the fall. Get to the point with the tech transfer office that there was some interest in further protection for the intellectual property that they disclosed. Sadly, in all three cases, it didn't actually end up generating any patents, but additional documentation was produced and additional scrutiny was brought to bear and lawyers got involved. And so there was at least a potential for patents. And sadly, upon additional review, it turned out that the things that we had thought were inventions for whatever reason were not. But that doesn't mean that won't change in this semester. So that's the process. And hopefully it's not too complicated or convoluted. But that's what you guys will be doing for the IP disclosure, which is due on the 26th. So let me just stop there and ask if anyone has questions about that assignment. Okay, seems like we're okay. So if you have questions, feel free to email me or come to office hours, which happened after class today, and I can kind of talk through in more detail how to submit this in a way that reduces the amount of time that you have to spend doing it to the bare minimum possible for us to just make sure that we've got all the T's crossed and the I's dotted with respect to IP disclosure, so that we don't end up getting missing something, right? Missing an opportunity to protect intellectual property that you guys invent. Okay, so I think we've got that wrapped up. On to the second thing, which is an example of quantitative engineering analysis. And so this feeds directly into, or I guess comes directly from the preliminary design report, which is what you guys are working on now. And so I took this excerpt right from the PDR just to show you kind of where this fits in the overall report. So in the preliminary system design analysis section of the report, it starts out with concepts for each subsystem selected in the above section, which by the way is the down selection section. This report section presents detailed engineering analyses showing how those concepts synthesize into a working prototype. And then there's some description. And then this report section will include the following subsections. There's material selection, which you guys now know how to do from the Ashby plots and from Brandon's lecture on material selection for the 3D printers. And then this is the section that I wanted to highlight for today's lecture, which is the additional engineering analysis of selected design to refine parameters and develop CAD models. And then, as I said in the beginning of class, it's repeated here and underlined, at least one quantitative engineering analysis is required for each subsystem. So if you have 6 subsystems, you'll have to repeat this type of analysis 6 times. So you have 6 different analyses for 6 different subsystems. And let me, I guess, also preface this by saying you don't have to analyze like the entire subsystem. Like, that would be nice, but you don't have to. Really what I'm interested in is just an analysis that helps you, as I say here, refine parameters and develop CAD models. And so really what we're looking for are, if you select a part and there is a dimension, a critical dimension in the part, some sort of analysis that informs the selection of that dimension, or the selection of a combination of dimensions that makes a feature that then gets embodied in the drawings and the CAD model. So that's really what we're after here, is an analysis that informs how big a part is, how thin a part is, how long a part is, just dimensions of parts. And you only have to do one. You're welcome to do more for sure, but only one is required. And again, kind of looking back over the history of the reason that this is in here is because we expect students to do this anyway, but in the past a lot of students have not done this. They've just sort of done the rule of thumb, or I'm just going to make a guess type approach to setting dimensions. And then when you get into the final design oral presentation, and the engineers from Cummins or Northrop, when they ask like, why is this dimension what it is, and then you get like crickets chirping, you get no good solid answer, and that's not great. So we want to make sure that you guys have got really good, strong, solid answers and explanations for why you've selected everything when it comes down to the final panel, which is why we've asked you to do this now, so that you're well prepared to answer those questions when you're in front of the panel. So the example that I wanted to give, you guys know I'm a thermal fluids guy, kind of pretending to be a design guy. And so this is one of the 3D bioprinters from the fall. And the thing that was really compelling about this one, it was called the turbo cell printer. The one that was really compelling, or the thing that was really compelling, at least for me, was this feature here. So this was the cell deposition and extraction subsystem. So you can see kind of circled in blue here was that overall subsystem. And what this did was it essentially provided either a positive pressure or a negative pressure that fed through this line, which is just, I think, Tygon tubing, so plastic tubing. It just fed through this line into the 3D bioprinter, and then it's very hard to see because this is a kind of a not perfect isometric, but there's a little needle sticking down here. I think you guys can see my mouse. There's a little needle sticking down here. That was the actual deposition tip that deposited the cells and extracted the cells from the liquid-like solid in the well on the microscope, right? So you can see the microscope mount here. And so this line, this Tygon line, fed all the way into that syringe and down into feeding the needle. And what these guys did is they took some cells and sucked the cells up into kind of a syringe that's sitting in here, and then they moved the 3D printer over the well on the microscope, dropped it down into the LLS, and then with positive pressure from the pump, pushed the cells that they had previously extracted with negative pressure down into the LLS, and that's how they did their deposition. So it was a centrifugal pump as opposed to like a piston, or there's a couple other ways that you can do this. You guys have invented tons of ways in your CDRs to do this, but that was how they did it. And so the issue was that the volume flow rates were so low. I think it was something like I'm trying to remember, it was like 1 microliter per minute or something like that. But anyway, the volume were so low that these guys could not find a commercial off the shelf solution to do this. And in their down selection, they had ultimately decided that they wanted a pump. A pump was the solution that came out of down selection that had the highest scores, but they couldn't find one that was commercially available, that was small enough and had a low enough and controllable enough volume flow rate to make that process viable. And so they ended up just designing their own, which I thought was very cool. So that's why I'm highlighting this one, because it's a really cool like fluids application. So before I jump into kind of how they did this analysis to help you guys inform your analyses, I do just want to point out kind of a side aspect of this, which is called Maslow's hammer. And at least in our case, Maslow's hammer refers to the selection between OTS, off-the-shelf parts, and custom parts. And so what Maslow's hammer says, it's basically a quote by A.H. Maslow, who wrote this book, Towards the Psychology of Being, in 1962. But interestingly, versions of this quote are attributed all the way as far back as the 1800s to Mark Twain, to Samuel Clemens. But essentially, and you guys have probably all heard this, essentially what it works out as is if you have a hammer, every problem looks like a nail, is kind of the simplified version of it. But what Maslow said in his book is quote, "I suppose it is tempting, if the only tool you have is a hammer, to treat everything as if it were a nail," unquote. And so I've just got this, kind of clip art picture here of a hammer and a nail to accentuate this point. But effectively what this means is if you have an easy, ready, known, available solution, you start to think of all of the problems that you encounter as being solvable by that particular solution, right? So in this case, your solution is the hammer, and any problem that you encounter starts to look like a nail, in that, hey, if I can just stand it up and whack it on the head and, drive it into the board or whatever it is that I'm trying to assemble, that solves the problem. And from a design perspective, this thinking is a bit dangerous, in that, as you guys are discovering, a lot of problems are not nails, right? A lot of problems are more complex than nails, and I'm using nails as a metaphor here, but more complex than nails. It's not like you can just pound on something enough and you've solved the problem. And so I found over teaching this class, at least at UF for the past year, that this decision between off-the-shelf parts and custom parts very much resembles Maslow's hammer, in that in the 21st century, we have McMaster-Carr and Amazon and various other online portals where you can literally go on, type in a few keywords, and there at your disposal appears every possible hammer, again, as a metaphor, every possible hammer that you can possibly imagine, just ripe for the picking, right? So there's a very strong inclination among 4501 students to design around off-the-shelf parts, because you can literally build up your entire design out of parts that you buy off of McMaster or Grainger or Amazon, without ever having to fabricate anything, right? And of course, that's easier, quote unquote, because you don't have to come up with any drawings, because McMaster has all the drawings. You don't have to worry about tolerance loops, because the drawings are already done for you. The parts are prefabricated. And so in a lot of ways, students tend to gravitate towards this because it's seen as a less expensive and easier solution than designing and fabricating custom parts. So all that is true. And I'm not saying to totally avoid OTS parts and start, machining your own screws and your own nails, because that would also be ridiculous. But what I want to just make everybody aware of is that by fixating on McMaster or Amazon, by looking for OTS parts, you are constraining your design options. You're reducing the size of the design space by limiting yourself to only what's already out there. And so please use McMaster and Amazon for, like I said, things like, fixturing, nails, screws, nuts, all of the basic stuff. And, certainly consider it as an option as you're looking for, other parts and components. But particularly for parts that have novel function, I would really strongly encourage you guys to not just go on an archaeological dig through McMaster or Amazon to try to find a part that satisfies a novel need, because what invariably will end up happening is students will find something in McMaster, something in Amazon that's like close to what they want, and they'll go in and actually change their design, modify their design so that it fits with what they can purchase from McMaster. And in the process of doing that, they actually diminish the function of their original design. So they make that trade-off between it's easy to buy something commercial off the shelf, and so I'm going to reduce the capability of my design, reduce my ability to delight the customer, so that I can just very easily buy a part commercial off the shelf and include it in my bill of materials and be done, and not have to worry about custom manufacturing. So in this case of the pump, this is exactly what happened. Is these guys were desperately looking for pumps from McMaster, from Amazon, from pump manufacturers all over the place, and they spent a ton of time trying to do that, only to find that there was no rotary centrifugal pump that was available as small as they needed it to carry out this function that they had identified of, I think it was 1 microliter per minute, based on the customer needs, to pump the fluid at a rate that would produce the feature sizes that they needed. So in a way, this is sort of a cautionary tale of kind of what happens with Maslow's hammer. And happily, they ended up not modifying their design, but instead going through the process of actually designing the pump. When you guys are sort of thinking about like which part you want to do this analysis on in your preliminary design reports, it really should focus on parts that have some sort of novel function, something that is not fitting or fixturing, or something that's novel. And each one of those subsystems does something novel, right? Otherwise they wouldn't be subsystems. And so a lot of times you'll find that the part that students analyze is the one that actually carries out the novel feature of the otherwise kind of boring subsystem, and everything else in the subsystem is just like balance of plant, right? It's like the structure and the fixtures and everything that hold it together. Okay, so let's kind of jump into this in a little bit more detail. This is the fluids part. So I love design and I get super excited about design, but with fluids, it's like turning it up to 11, right? So it's like fluids, right? So I go a little crazy because I love it so much. Okay, so this was the subsystem that they were looking at. They ended up actually designing. We never built this thing, but they ended up designing this 3D printed micro pump. The front and the back housing were held together by screws. So you can see the screws right there that did that. And there was an inside impeller that was sealed by an O-ring. And I've got a cutout view to show you guys in a second. This whole thing was manufactured, or was intended to be manufactured by photocurable resin. Resin 3D printing process. And they wanted ultimately to, because remember, this thing is pumping fluid into the 3D printer and out of the 3D printer. So they wanted to fit a Tygon tube over both the inlet and the outlet. And so they ended up adding a 1/16 inch tubing attachment, like a barb attachment to the inlet and the outlet of the pump. So that's that barb that's 3D printed in there so that they can do that tube. Hose barbs ensure the pressure would separate the hose from the pump before anything yielded. So they did a failure analysis on this thing, which I won't show, to make sure that the pump itself didn't explode, that the hose would actually pop off before the pump overpressured and exploded. And then they selected a material to make this out of that could be sterilized with bleach or ethanol. So you guys recognize that the customer need there of all the parts needing to be sterilizable. So that was kind of where we landed. Here's that cutout that I was describing. So they have an impeller. This is a centrifugal pump. They have, there's a comment. Yeah. Okay. So let me pause. That's a good question. And this in a way goes back to, so for those who can't read the chat, this is Sheng Zhao has asked, does the MAE department provide resin printing facilities that we could access? I am curious for where they made the part. Yeah, so if we go back just for a second here, back to Maslow's hammer, the department has the ability to make anything that can be made. So if you need something that's resin printed, 3D printed via resin, we have that capability. We have filament deposition 3D printing, we have CNC mills, we have manual mills, we have lathes. We can even, to some extent, even do some casting if you want. So yeah, so the department has all of the capabilities, all the manufacturing capabilities that you could possibly want. The only thing that we don't have is injection molding. The beauty of injection molding is that anything that can be injection molded can also be 3D printed. And so anytime we needed an injection molded part, we've just 3D printed it with a filament deposition 3D printer. So yeah, we do actually have a resin printer, and if you needed to fabricate this using that technology, that's what we would do. We would just, basically give it to you guys probably all know Carl Crane, Dr. Crane. He's the one that controls all the 3D printing capabilities in the department, and controls is a very strong word. Oversees is better, oversees all the 3D printing capabilities. And so ultimately, if it was not something that we could do in the Merge Lab, we've got a whole print farm of filament deposition 3D printers. If it's something that we could not do, we would just outsource it to Carl Crane, and he would get it done for us. And then even then, in an even worse situation, like for example, in the past, students have specified parts that needed to be powder coated, and we at least in the department do not have a powder coating capability. In that case, we would outsource it to a job shop in Gainesville. So literally, when we were making the upper tone, which was the exercise machine that when Mike Griffiths taught 4502 in the fall, most of those components had to be powder coated, and they were big, right? This is like a human-sized exercise machine. We just loaded all of the metal parts. We fabricated all the fabricated all of the metal parts into their final form, and then Noel Thomas, who's the TA for the teaching technician for the class, loaded them all into a truck and drove them off to a powder coating facility in the northern part of Gainesville. So even if you end up designing something that cannot be fabricated at UF, we have the connections in town, and happily Gainesville has a pretty robust manufacturing capability just in the local businesses, the local companies. We would just outsource it if we couldn't do it in-house. So yeah, I guess to answer your question, anything that you guys design that can be built, we can get built for you for 4502. So don't use or don't worry about the constraints of manufacturing. If you need a particular feature in a design, go ahead and put it in there, and we'll figure out a way to get it built. Yeah, no problem. Yeah, no, but good question, right? Because that's another part of Maslow's hammer, right? Is if you guys don't have or think you don't have the capability to manufacture something, you're actually going to change the design so that you can manufacture it, which happens in industry all the time. But in our case, I'd much rather have you meet the customer needs and have customer needs that are really high on the or deliverables that are really high on the customer satisfaction scale, and pay a little bit more to outsource something rather than to change the design to try to do it in-house. Okay, so let's pop back into this one. So let's see, we talked about the impeller. Okay, so here's a cutout. Here's the impeller. Here is that O-ring that you can see. So the impeller is sealing against the O-ring, which is preventing leakage through the shaft. And it's a centrifugal compressor, or centrifugal pump. So you guys who have taken either a fluids class or thermo fluids lab with John Abbott are familiar with how these work. But this is the shape. It essentially spins, and fluid is brought in through this this channel here, and then it's spun centrifugally outwards, and then it's pushed out of. Let me pop back. It's pulled in here, and then it's pushed out through here. Yeah, that's funny. They've actually got it turned the wrong way. Huh. Anyway, okay. So anyway, so that's how it works. Is that the fluid is drawn in here, and then this thing spins and adds momentum to the fluid, and then it gets pushed out. And then, sorry, somebody just made a comment which came across, and then I lost it. Okay, so Josiah is asking, is there a limit on how experimental the manufacturing technique? No. Anything that exists in the outside world that's a manufacturing technique that you can find is fair game. So if you need something that's really exotic, if you need EDM or something that's unusual, and the feature that you need can only be manufactured through that technique, go ahead and specify it anyway, and we will figure it out. Even if we have to, send something out to a Jacksonville or someplace that has even more manufacturing capabilities than Gainesville, we'll figure out how to get it made for you. So don't use limitations in manufacturing capabilities to govern the parts that you guys design. Design what you need, and we will figure out a way to get it built. Yeah, no problem. Yeah, no, that's yes, it's I I think super important that you guys not be constrained by manufacturing. If there's a technique out there to build what it is you need, please just specify the dimensions you need, and we will figure it out. That's what 4502 is for those guys to figure out how to make all the stuff that 4501 students design. Okay, so let's see, outer radius of the blades. Okay, so the outer radius of the blades was determined, and I'll show you guys this by Euler's pump equation, turbine equation, and desired flow rate. And so ultimately, the question that they are answering. So this was the question that ended up in the preliminary design report. It was determined the needed rotation rate for a tiny centrifugal pump pushing water at 1 microliter per minute through a 1 meter long capillary tube with a diameter of 1 millimeter. So if we, let me just grab these words and kind of come back over here and maybe paste them. Hopefully this doesn't destroy. Okay, not too bad. Okay. So we'll just stick that right there. Okay, so what they were worried about is the smaller these pumps get, the faster they have to spin to achieve a particular desired volume flow rate, right? Because there's less volume in the pump, right? So you have to move the volume in the pump faster to get a desired volume flow rate. And so the worry was they were going to make this pump so small that the motor that would have to turn it would have to rotate so rapidly that it would basically be impossible, that there'd be no DC motor, even that you could imagine, that would rotate so fast that it would do the job of pumping. And actually, interestingly, this is an aside, real quick aside, but my kind of main area, I do a bunch of pedagogical research, but I also do thermal fluids research. And my main research area is actually Tesla turbines. And Tesla turbines are pretty much the fastest rotational prime movers that like exist before like ball bearings and things start breaking down. And so for a while they had actually imagined, this would have been super cool if it had worked out this way. They imagined using a Tesla turbine here instead of a DC motor to turn this pump, because they had originally anticipated something like 100,000 or 120,000 RPMs, which is way faster than a typical DC motor can turn. And so the original design actually called for a Tesla turbine here. And so I was just over the moon, because that's like my research area, and it's fluids and it's design. It was like, how could this possibly get any better? But it works out, as you guys will see in the calculations, that they did not need something as exotic as a Tesla turbine to achieve the needed volume flow rate. But that was the question: is how fast do they need to turn this thing in order to get the 1 microliter per minute volume flow rate, and then through a meter long capillary tube, right? So here's that capillary tube, nominally 1/16 inch inner diameter, which I think corresponds to a millimeter inner diameter, that connects onto the hose bar. Connects onto the hose barb here, and then connects back into the 3D printer there. And it has to be a meter long, because, as you guys well know from the customer needs, you can't have anything that's vibrating that's sitting on the microscope or on the laser table that the microscope is sitting on. So they had to have this sitting off on a different table that was, the run of tubing was at least going to be a meter long. And so that's where they got all those parameters from. So that was the question that they asked for this particular subsystem in their preliminary design report. And so this is a fluids problem, right? Yay. So how did they tackle this? Well, with fluids analysis. And so they started out with just a generic pump. So you guys recognize this, hopefully, from your thermal class, as a schematic representation of a pump. And this is an energy balance on that pump. And so the fluid is coming in through the reservoir, and then centrifugally getting momentum transfer, energy transfer, getting spun up, pressurized, and then pushed out of the pump here, and then down this tube at 1 microliter per minute. So, of course, to do this type of analysis, you can get arbitrarily complex, but we always like to make, as engineers, simplifying assumptions so that we can solve the problems that have been thrust upon us. And so we assumed no major losses in the pipe or the pump fittings. And that's interesting. Major losses. This should be minor losses. No minor losses. Huh. Okay, no minor losses. So if you guys remember from fluids, minor losses are the losses that come from having like bends in the pipe, or valves, or contractions, or expansions, nozzles, those sort of things. So we assume that there was none of that, that the run from, the pump right into the 3D printer was just one straight shot of Tygon tubing without anything interfering. We also assumed that there's no elevation change, so we didn't have to worry about the pressure head associated with hydrostatic pressure. We assumed that the fluid going through was water, and that it's incompressible. We also assume that the pump does not heat up, essentially that its efficiency is 100%. And so any energy that you put into the pump ultimately would be expressed as it's actually an enthalpy, but it's basically PV work, right, of fluid flow coming out of the pump. We imagine that the capillary tubes were perfectly smooth on the inside, which is not a bad assumption given that Tygon is almost atomically smooth. So that's a pretty good assumption. And then because we had a centrifugal pump, it turns out that the velocity, tangential velocity at the inlet, you guys will see I've got the velocity vectors on the next slide. Or well, 2 slides out, that's effectively 0 for a centrifugal pump, right? So the fluid comes in through the inlet, it makes this 90-degree turn, and then it's in the pump. And so that 90-degree turn basically gives you 0 tangential velocity as your fluid is entering the pump, because the fluid is entering perpendicular to the tangential direction. So that component of the velocity is 0. Okay. So, and this should all be like super familiar from your fluids courses. So what did they do? They needed to figure out how much pressure was required to do this pumping job. And so they used the Darcy-Weisbach equation, which I'm sure you guys remember from fluids. And here's that equation, right? So it's literally just I hate to say this, it's a modified Bernoulli's equation, and you guys know that Bernoulli is super dangerous. So be scared of Bernoulli, but Darcy Weisbach actually modifies Bernoulli with a friction factor that's empirical, right? So this is actually now a correct representation of the pressure loss in that tube because the friction factor is there. So L is the length of the tube, rho is the density of the fluid, D is the diameter of the tube, and V bar is the average velocity of the fluid running through the tube. And if you put all those together, you end up with a change in pressure from the inlet of the tube to the outlet of the tube, which is the pressure that they had to overcome at the set volume flow rate to get the desired need of the fluid moving at 1 microliter per minute. So the fluid flow is very likely going to be laminar, but let's just check. So we need a Reynolds number, and to get a Reynolds number, we need a velocity, an average velocity. So we know the volume flow rate, 1 microliter per minute. Volume flow rate divided by cross-sectional area is the average velocity. So the velocity times the cross-sectional area is the volume flow rate. And so we go through and just kind of reconstruct this guy to give us a velocity, and we work to a velocity of, it's really low, 0.00127 meters per second. With that velocity, and knowing that the fluid, at least initially they thought the fluid they would be pumping was water, they calculated the Reynolds number, and it works out to be 1.4, right? So this is like Stokes flow almost. This is like super low Reynolds number flow. And so very clearly the flow is laminar. Whenever I show a Reynolds number, by the way, I always just like to prove to myself that the result is dimensionless, right? Because that's a very easy kind of sanity check to make sure that you haven't done something wrong. And so here I'm just converting the newtons in the viscosity into kilograms per second meter, so I can show that this is dimensionless, which it is. It works out to be dimensionless, so that's fine. You guys probably remember from your fluids class that a Reynolds number less than about 2100 gives you laminar flow. 1.4 is very much less than 2100. So yes, we have laminar flow, which means we can use the friction factor just based on 64 over the Reynolds number. And just to remind you guys, you've seen this in fluids, this is a Moody diagram, right? So we've got Reynolds number on the x-axis, we've got friction factor, that F value that I was just talking about for the Darcy-Weisbach equation on the y-axis. And so long as you're in laminar flow, which is, again, Reynolds number below about 2000, you're just in the 64 over the Reynolds number regime here. Oop, hang on, somebody made a comment. Let me see if I can get back to that. Okay, oop, hang on, let me just read this. Can Derek, read this to everybody? Okay, so Derek is asking, the bioprinter needs to be able to extract and also dispense cells, but from what I can tell, centrifugal pumps only pump in one direction. Did the customer needs not require cell extraction for this semester, or did the design extract cells using a different pump? We did not. I got to think about that for a second, because that's a good question. I'm pretty sure. Well, okay, so they definitely had to get the cells into the syringe to begin with, right? So even if there wasn't an extraction requirement, there had to be an extraction of some kind from a reservoir to get the cells in there, because it was otherwise a closed system. So that's actually a good question. I'll have to go back and check. Carly was the student. I'm trying to remember Carly's last name. Anyway, she was the student that designed the pump. And so let me check. Let me write that down. I don't remember if anybody even asked her that question. Extraction. Yeah. Ha. Okay. So that's a good question. I don't know the answer off the top of my head. I don't know how they did the extraction. But let me follow up with Carly and ask her, because yeah. Let me before I say something that's wrong, let me ask her. So yeah, keep that in mind. I'll follow up and find out. But yeah, that's an interesting point. That would have been kind of a deal breaker. Now I'm interested in how they did the extraction. Huh. Okay. Anyway, sorry. If I spend time thinking about it, we'll run out of time. And we've only actually got about 6 minutes left. So we'll put that one on hold, but I'll figure out and get back to you guys. Okay. So Reynolds number, friction factor. So here's 64 over the Reynolds number. We're like way over here, right? We're way into really low Reynolds number flow. And so 64 of the Reynolds number is the friction factor that we can use. They then put the friction factor 64 over the Reynolds number, and we know the Reynolds number, right? It's 1.4 into the Darcy-Weisbach equation, and out popped the pressure. And so the pressure that was required to do at least the deposition process, and I got to check on the extraction process, was about 37 pascals, right? So not a lot, but also not trivial either. And so once you know the power and the volume flow rate, not the power, the pressure and the volume flow rate, you guys remember from thermo that volume flow rates times pressure is the power that's required, pumping power required. And so you can use the knowledge of the pumping power required and Euler's turbine equation to back out what the volume, what the rotational velocity of the blades need to be in order to achieve that pressure at the selected volume flow rate. And so here's from thermo, Euler's turbine equation. I bet, I don't know if this would be in thermo or maybe in fluids. In one of those two classes, you guys are probably looking at this thinking to yourselves, I thought I'd never have to see this again. And here it is, in all of its glory. So the Euler turbine equation just takes the product of the input velocity vectors, subtracts that from the product of the output velocity vectors, dimensionalizes with density and volume flow rate, and that's the power required to pump fluid and achieve those velocity vectors. And so this power, which I represent as pi, is the same as this power, which is the torque times the rotational velocity, but also the pumping power, right? So the change in pressure multiplied by the volume flow rate. So all those pi's are all the same. They're all power. And so you can see pretty quickly, you can start to manipulate these equations, add mass conservation, and give yourself an equation for the volume in the radial direction at the outlet of the pump. And then if you take all of those equations and combine them together, and I'll post this if you guys are interested in this, I'll post it up on Canvas so that you guys can see it. Combine all those equations together and ultimately get this expression here, which is the change in pressure with just all of the key things that you need in it, right? So it's got that rotational velocity, it's got the radius of the pump, and then it's got that tangential velocity. And then because you have an expression for the tangential velocity from the previous substitution, you stick them together and you get this expression that has just everything in it with only one unknown, and that unknown is the beta angle, so beta 2, which is the angle that the impeller blade makes with the outer radius of the centrifugal pump. And if you guys look back at the design, this centrifugal pump, it basically had a straight blades, right? So Carly didn't try to put any curvature into these blades, and therefore beta 2 is 90 degrees. The cotangent of 90 degrees is 0. And so everything just sort of collapses out of the equation, and you end up with an expression that relates everything that you know to the rotational velocity. And so how did this ultimately inform what the students what the students needed to know, which was, could they come up with just a DC motor to drive the system, or did they need to do something like add a Tesla turbine or something more exotic? Here I'm just showing that the dimensions work out as they should. Rotational velocity is rotations per second, 1/2. And so it works out if you plug in all the numbers, the pressure, the density of water, the radius of the pump that they were talking about, you end up with only 2,300 revolutions per minute. So well within the range that's possible through a DC motor. And so that was the analysis that they included in their PDR, which was awesome. Like this, this is fluids, and I loved it. Fluids and design together is like, how can you get any better than that? So in the last moment here, given that, now we know that we can attach a DC motor to this pump and run the pump and get the pressure that we need and the volume flow rate that we need, what do you guys think was the primary criticism from the panel? Uh-oh, everyone's asleep. Oh, go ahead. Go ahead. Someone's going to say, oh, life cycle. Okay. Oh, that's an interesting one. Yeah. Okay. That's a good point. That was not the criticism that I had in mind, but yeah. How many hours can you run this thing before something breaks on the inside, especially because it's resin 3D printed? Yeah, so that's a viable criticism for sure. The one that I thought you guys were going to say to be funny was how do they extract the cells, right? Which was already brought up. Any other thoughts on the key criticism? I'll give you a hint. It happens right here. The interface between, let's see. Yeah, no, okay, yeah, assembly, that's very small parts for sure, so it would take a long time. Yeah, there you go. It would take a long time to put this thing together because the smart parts are so small if you think about Boothroyd and Dewhurst. But yeah, it was how to, so Hunter's got it, how to mount this tiny, tiny, tiny little pump to this DC motor. And by the way, this DC motor was like the smallest one that they could find that had that 2,300 RPM capability. And the motor is like huge, right? It's enormous, even though it was like the size of a dime, right? It's enormous compared to this pump. And so the concern was if and think about like the tolerance loops, right? And the tolerance that would be required, this structure that the pump is sitting on, if it is, just off by like a micron in either direction, you're not going to be able to align the shaft of the DC motor with the pump. You're going to get wobble, and the DC motor is literally going to rip the pump to pieces as it tries to spin the pump up to full RPM. So that was the criticism that came out of the panel for this particular design. So a couple of you guys, and I notice I'm a minute over here, so let me wrap this up here in just a second. The last comment that I want to make is to recognize that you guys had asked about manufacturing capabilities and whether this was built or not. We ended up not building this. We didn't select this one and didn't build it. Specifically for that reason, for the concern about how the pump would actually be mounted to the DC motor in a way that eliminated the vibration or the wobble if you happen to mismatch the motor to the pump. But yeah, the concerns about how to extract the cells, nobody even thought about that one, so that was a good one. And then lifetime for sure is another issue. Like, this thing is super small, it's made of resin, it's spinning super fast. How long would it last? So that's a concern as well. Okay, so let's stop there because I'm over time by just a minute or two. The last thing that I wanted to kind of throw out there was this team cross-pollination activity. I will communicate this to you guys over email, so you guys will get it that way. It's not it was going to take a minute to explain, but we're over time, so let's stop there. Okay, I'm done. Can I answer in a moment or two any final questions? And just remind everybody that I have office hours in 15 minutes. So any questions that are long can be asked in office hours. Any short questions? Okay, seems like no. So let me stop recording. Stop.